In this video, I want to consider a few special trigonometric limits. I want to look at the limit as x approaches 0 of the sine of x over x. So here's a graph of the sine of x over x, and we see that at 0 we have an open circle here. It's not defined there, but it looks as if the function is approaching 1 as x approaches 0. And the second limit I want to look at is the limit as x approaches 0 of the cosine of x minus 1 over x. And here's a graph of that function. And again, it's undefined at 0, and it looks like the function is approaching 0 as x approaches 0. Now this was just a graphical approach here. I want to actually try and show the values of these two limits, and we'll start with the first one, the limit as x approaches 0 of sine of x over x. And the reason I'm interested in these limits is once I find the values of these limits, it allows me to find the values of other trigonometric limits. Okay, so to begin with, we're going to look at the limit as x approaches 0 of sine of x over x. And the discussion here, it's going to be a little bit of a long discussion, but the steps are not that difficult, so bear with me here. So first, we're going to assume that x lies between 0 and pi over 2, just to make things simple. And I'm going to look at an arc of a circle here, and this is a circle with a radius of 1. And I'm going to draw this line down here, which is going to be perpendicular to one side, and then I'm going to draw the line that connects the other two ends here. And so let's label some things here. This angle I'll call the angle X, and then I'll label this point A, B, C, and D. Okay, so that's the diagram that we have. And the first thing we can note is that the measure of the arc CD, that's this outside part here, this arc, is equal to x. That's the central angle right here. And the sine of x is BD over AD. Where does that come from? Well, if you think of SOHCAHTOA, sine is opposite, that would be BD, over hypotenuse, that would be AD. And then I can rearrange that to say that BD equals AD times the sine of x, but that's just equal to the sine of x, because remember that this is a sector out of a unit circle, and AD has a length of 1. Okay, so now note that BD is less than CD, which is less than the measure of that arc CD. So let's think about that. Here is BD, okay, and that's definitely less than CD because this is a right triangle here, and the hypotenuse is always the largest side of a right triangle. And then that's less than the measure of this arc. Well, that makes sense. This arc is definitely larger than this distance CD. And if I look at the outside parts of this inequality here, the BD and the measure of the arc CD, then I get this. Well, BD is equal to the sine of x, and the measure of arc CD, that's just equal to x. So I have sine of x is less than x. Now I can divide both sides by x, and I get the sine of x divided by x is less than 1. And that's my first inequality that I'm going to use to evaluate this limit. So if you haven't figured out what's going on so far, what I'm trying to do is to use the squeeze theorem on this limit by putting bounds on sine of x over x. So I already found out that sine of x over x is less than 1. Now I want to find something for the other side of the inequality, and then I'll apply the squeeze theorem. Okay, so we found sine of x over x is less than 1, and here was the diagram that we had before, and I'm going to change it a little bit. So I'm going to get rid of this line that goes down, that perpendicular line, and instead I'm going to extend this out and make a larger triangle. And then I'm going to add this line here to make another right triangle. And so I'll label this point E and this point F. And again, remember that x is assumed to be between 0 and pi over 2. Okay. So the measure of arc CD is less than CF plus FD. Well, let's look at that. Here's arc CD, and then CF plus FD. Yes, that does appear to be larger than the arc. And that means that x is less than CF plus FD, because remember the measure of arc CD was just x. And that means x is less than CF plus FE. So all I did was replace FD with FE. Well, if you think about it, here's FD. FE is definitely larger than FD. This is a right triangle, and FE is the hypotenuse, and the hypotenuse is always the largest side of a right triangle. So if x is less than CF plus FD, x is certainly less than CF plus FE. But CF plus FE, that's just this long side of the big triangle here, CE. Now the tangent of x is CE over AC. So remember by SOHCAHTOA, tangent is opposite over adjacent. So here's x. I'm looking at the big triangle now. The opposite side, that's CE, and the adjacent side, that's AC. So this is opposite over adjacent. And I can rewrite that as CE equaling AC times the tangent of x. But what's AC? AC is just 1, so this is just equal to the tangent of x. So now I have that x is less than the tangent of x. That's going back up to here. X is less than CE, but CE is the tangent of x, so x is less than the tangent of x. And I can rewrite tangent as sine over cosine. And then I can rearrange this inequality as the cosine of x is less than sine of x over x. And remember, x was assumed to be between 0 and pi over 2 here, so I don't have to worry about x being negative at all. So I don't have to worry about switching the sign of the inequality. All right, so now I have my two inequalities. So I have sine of x over x is less than 1 and cosine of x is less than sine of x over x. I can combine these into one inequality. And remember, x is between 0 and pi over 2. So that means x is positive. So I'm going to look at the limit as x approaches 0 coming from the right of each of these. So we have cosine of x, and the limit as x approaches 0 coming from the right of cosine of x is 1. And of course, the limit as x approaches 0 coming from the right of 1 is 1. So that tells me by the squeeze theorem that the limit as x approaches 0 coming from the right of sine of x over x is 1. But remember that f of x equals sine of x over x, that's symmetric about the y-axis. It's an even function. So that means that the overall limit coming from either direction, x approaches 0 of sine of x over x, has to be 1. Okay, now that was a pretty complicated argument, and as long as you were able to follow all the steps, that's fine. You don't need to be able to reproduce all the steps. Just make sure you understand where they come from. And now that we've figured out this limit, we can work on the other one. So we have the limit as x approaches 0 of sine of x over x equals 1, and we want to look at the other limit, and this one's going to be a little bit easier. So we have the limit as x approaches 0 of cosine of x minus 1 over x, and I'm going to start by multiplying top and bottom by cosine of x plus 1. This is a similar trick that you use with square roots and complex numbers where you want to change around the expression you have. And when I do that, I get a cosine squared x minus 1 up top, and then just the same thing, x times cosine x plus 1 on the bottom. And then I have negative sine squared x on top. Where's that coming from? Well, if you remember, we have the sine squared of x plus the cosine squared of x is equal to 1. That's the Pythagorean identity. So cosine squared x minus 1 is equal to negative sine squared x if you just rearrange this. And I'm going to break it up so that I have the negative pulled outside, and I'm going to break up the sign. So I have one of the sine of x's over x, and the other sine of x over cosine of x plus 1. And then I can use one of my limit laws here to break this up into two different limits. Remember, you can only do that if each of these individual limits exists, and it turns out that they do. So this is we're allowed to do this here. Now that first limit, sine of x over x, that was 1. That was the limit we found before, and so with the minus sign that's out front, that's a minus 1. And then the second limit, as x approaches 0, well, this is 0, cosine of x approaches 1. We have 0 over 1 plus 1, and that's just 0. So now we have both of our limits, and you can use these two special trigonometric limits to evaluate many other limits that involve trigonometric functions.